Hey guys, welcome to week 4. Everyone did really well on the midterm. That is, everybody who took the midterm. For some reason, some people didn't take the midterm. I guess they're probably the same people that stopped trying in week 1 of this class. But anyway, that means that the review was helpful and that you're doing the reading and that you're studying and that you are applying yourself. So good job for all of you who, most of you scored above 80%. There's a few down there who maybe didn't watch the review or didn't read the material and they took the midterm and didn't get an 80 or percent or higher. But hey, you know what? That's the way it goes. Good job. Today we're going to talk about file slack this week. That's kind of a topic of conversation for this week's class. And in order to understand file slack, you need to understand basic hard drive architecture. And what we're talking about is the old platter-based kind of legacy hard drives, 3.5-inch hard drives. I still have, 2 terabyte hard drives in my stack in my workstation. Most people have a hard drive or a solid state drive as their operating system these days. So my OS drive is a solid state, but all of my data drives, because they're so much cheaper, are these old legacy platter hard drives, right? And here's a diagram here for those of you that like to visualize things. You've got these, excuse me again, sorry. You've got these literally metal discs, little metal pancakes stacked on top of each other. I guess if you took a CD or a DVD, they're close to the same size, and only they're metal, and you stacked them on top of each other on a spindle. And you've got a read-write head that can go out and kind of hover over the various tracks and sectors on the two heads of each given platter and read the data that is stored there electromagnetically. So the smallest allocated space on a platter is formatted at the manufacturer, at the factory, and it would be, 1 byte. But you can't just write, well, 1 bit or 1 byte. So there's 8 bits to a byte. You can't just typically write to 1 byte. At the factory, they pre-format the hard drive into sectors, and they will designate a certain number of tracks on the hard drive. This picture here just shows 1 track, but in reality, there's dozens, if not hundreds, of concentric tracks from the center of the spindle out towards the edge of the platter. And there's dozens or hundreds of sectors on each track, right? So each sector has a certain number of bytes allocated to it at the factory. Now, typically, prior to anything bigger than a 2 terabyte hard drive, the standard has been 512 bytes per sector, and that's a really important number for later when we start figuring out file slack. You'll want to remember that typically there's 512 bytes per sector. Now, in newer, larger hard drives, they may have bumped that up at the factory level to be 4096 bytes per sector. But for today's, regardless of what the factory setting is on the bytes per sector, the concept is the same that we're going to show you today. So for today's presentation, we're going to say that there are 512 bytes per sector, which is still very common, and then we'll go from there. But this is your basic hard drive architecture on a legacy metal platter disk. All right. So, excuse me, here's another way of looking at it. Each of those tracks or rings on the previous slide has a certain number of sectors on it. It is also very, very common to group those sectors together into clusters, right? And so a cluster would then become, and this is file system dependent. When I take my partition on my hard drive, or I create a new partition on my hard drive and I format it as, say, an NTFS file system, I get to decide when I format it if I want to use the default, which is typically 8 sectors per cluster, or if I'd like to change that to just 1 sector per cluster, or 2 sectors per cluster, or 16 sectors per cluster, right? It's totally arbitrary. It's up to me. The default is 8 sectors per cluster, which gives us a typical cluster size of 4096 bytes per cluster. Now, at that point, the cluster becomes the smallest allocated chunk on a hard drive. It's the smallest piece of real estate that a file can use when it's written to the hard drive, to the file system. Okay, so if you understand this, we can move on. There's 512 bytes per sector. There's usually 8 sectors per cluster, and that means there's usually 4096 bytes per cluster. Okay, so a little simple mathematics, some simple multiplication, and you should have that concept down. Now on the screen here above me, we have 5 clusters, right? And 5 clustered would be 5 times 4096, so that's going to be about 20,000 bytes, right? So this represented here above me is this would be a 5 cluster chunk, about 20,000 bytes or 20 kilobytes. So if I had a file that was 17 kilobytes or 17,000 bytes, it would fit in this chunk here on the screen, right? Those 5 clusters would be occupied by the data of that file. Now, the 17,000 byte file isn't going to fill up all 6 of the clusters. It's going to fill up, or all 5 of them, excuse me. Not all 5 of those clusters are going to be filled up by the file. Only the first 4 clusters there are going to be filled up totally with the data from the file. And then there's going to be a little bit of the file left over that fills up a little bit of that 5th cluster. Okay, so if you're not visualizing what I'm talking about, you'll get it in just a second. But what you want to understand, and let me shrink my big fat head here, get it out of the way, get down here in the corner where you belong, Professor. What you want to do is understand this concept that there's the logical file size, or it's the actual number of bytes occupied by the data on the hard drive, right? So if I have a very small, maybe it's like an icon JPEG or a .ico, a small graphic file, and it's 4,000 bytes, it's just 4 kilobytes, very small graphic file, right? That would all fit in one cluster, right? So that would fit in one cluster because one cluster is 4096 bytes, but it's going to use the whole cluster on disk in terms of how much space it actually takes up on the physical disk. Okay, so the logical file is 4,000 bytes, but physically on the disk, it's 4096 bytes. And often when you're looking at, say, FTK Imager and you're examining a file and you click on the file and then you look down the properties pane, right, it's going to give you a logical file size and an actual physical file size. And now you know what those two numbers represent, right? The 4,000 bytes is the logical file size, that's the actual number of data, and the physical is the whole cluster that it had to use on disk. Now, you could never write more than one file to a cluster. A cluster is always going to take the data from just one file. Now, you may have multiple clusters, in fact, you almost always do have multiple clusters that take up or that are allocated to a file, and you would never have those same clusters used by another file simultaneously, right? So clusters are always allocated to just one file at a time. Okay, so that's kind of a key point. All right, so how do we calculate file slack? Well, file slack is that leftover space from the end of the last piece of data of the logical actual file data to the end of the last cluster occupied by that data. So the file slack is the leftover space in between the file data and the last cluster. And so the formula is very simple. We're going to subtract the logical size of the file from the total number of clusters, or the physical size of the file, and that gives us our total file slack. All right, this is important. Why? Well, because there could be data hidden in that gray area up there, right? So if we're looking at this and we see, okay, we've got, remember we talked about that 17,000 byte file, okay? It's going to occupy all 5 of those clusters. Only the first 4 clusters are totally filled up. There's no file slack or any kind of slack in those first 4 clusters because they have data from the file in there. But that last cluster has a little bit of the file in it. Okay, and so all 5 of those clusters are the physical file size of that file on disk. But that last cluster has just a little bit of empty space or unallocated space. The space has been allocated to the file, but it wasn't used by the file. So that's what file slack is, right? So there's how we would, excuse me. So if I've got a 20,000 byte chunk of 5 clusters and my file is actually only 17,000 bytes long, then I know that I've got file slack of 3,456 bytes. Okay, so that's file slack. Now, the file slack itself is divided into 2 different kinds of file slack, and it's really kind of arbitrary, but it's worth noting. Okay, that the whole sectors at the end of that last cluster is called residual slack. Okay, or cluster file slack. And so you can tell by looking at this diagram that there are 6 of those 8 6 of those 8 sectors in that last cluster that have no data from my file in it, right? Because it didn't need that much. So we know that 6 sectors times 512 bytes per sector gives us cluster file slack or residual file slack of 3072 bytes. So there's 3072 bytes that might have old data from another file that's been overwritten. It's been deleted and overwritten. Or it might, could potentially contain hidden information. In my 6-7 years of doing computer forensics full time, never once investigating a hard drive did I find hidden data there. But could it be there? Yeah, it could. So we'd want to be aware of that. Okay, and then we've got this other little piece of this second cluster up here. And it has some blank space left in it, right? So it's got 128 bytes of unused space in it, and that would be called RAM slack. And the reason that's called RAM slack, and this is a legacy term, it goes back to the days prior to NTFS, when the operating system, when it finished writing a file, it would dump a bunch of RAM in there to fill up that last sector. I don't remember exactly why it would do that, but forensically, you might be able to find, if you're doing a string search and you found a password or an encryption key or something that was stored in RAM, and you found it in this file slack, in this RAM slack, you could explain to the jury, well, the operating system writes RAM to this last sector and that's why it's in there. Typically, operating systems don't do that anymore. They haven't done it since like Windows 95 or Windows 98, but that's still called RAM slack as kind of a layover from that era. And so we want to know, how do I, you're going to have to do probably some labs or some exercises this week, possibly that, and I have to look at them. I don't remember exactly, but you may have to calculate file slack or RAM slack. Certainly you'll have to know what they are. So here's how we do this, right? It's a very simple formula. I'm going to take the total number of bytes in all of the clusters. So I know, again, that if I've got a 17,000 or 17 kilobyte file, that's going to take up 5 clusters. But I know that there are way more bytes than necessary in 5 clusters. There's 20 kilobytes, so I've got about 3 kilobytes of total file slack. And if I do the math, if I say, okay, 4096 times 5 is 20,480 bytes total, and I know that there's 17,024 bytes in my file, then I just subtract those two things and I get the leftover, the 3 kilobytes, 3,456 bytes to be exact. That's my total file slack. Now, how do I figure out the residual slack versus the RAM slack? Well, the residual file slack is pretty easy to figure out, right? Because we know that there are 20,000 bytes total, and I'm subtracting 17,000 bytes. So I know that my total file slack is 3,456 bytes, but I don't know how many whole clusters in there. So that's a simple problem. I'm just going to divide 3,456 by 512, and 512 is going to give me 6 point something. And I don't care what the remainder is. I don't care what the point something is. I do care that there are 6 total whole sectors left. So I can say, oh, if I've got 6 whole sectors, that's 6 times 512, and that gives me my residual file slack of 3,072. And then, now that I know how many whole clusters are left over, I can subtract that 3,072 from the 3,456, and that gives me my RAM slack, or the leftover space in that last sector used by the file, of 128 bytes. All right, so that's a simple calculating RAM slack. Here's another visual depiction, a different way of looking at it, more linear, is I've got these 8 blue clusters up there. The 8 blue clusters represent 4096 bytes, but my file is only 1328 bytes. So the orange is my actual file, and it occupies 2 full clusters and a partial, 2 full sectors and a partial sector of the third sector. And so I'm going to take my total number of bytes in the cluster, 4096. I'm going to subtract the file from it, 1328 bytes, and that's going to give me, well, I don't do math well in my head, so let's pull up a calculator here. 4096 minus my total file size. Where's my total file size? Oh, there it is, the orange, 1328. And that gives me 2,768 total file slack, right? So my yellow and my light blue all together is 2768. And so I know that if I divide that by 512, it's going to give me 1, 2, 3, 4, 5 point something. Again, I don't care about the point something. That's the yellow. I don't care about that right now, but I do care that there are 5 total sectors left at the end of this. So I'm going to do 512 times 5, and that's going to give me a total file slack. Excuse me. Total. Total cluster slack of, so let's see, I want to remember 2768, and I'm going to say 512 times 5 gives me the 2560. Oh, I didn't need to do that math. It's written right here. 2560, right? And what was my, I've already forgotten what the original was. But I can figure it out again really easily by doing 4096 minus, yeah, I know, watching my ineptitude is cringeworthy. So total bytes in the cluster minus the total file size gives the 2768. Thank you. Here's my residual cluster slack right here, 2560. So if I subtract the 2560 from the total 2768, that gives me the leftover 208, right? So 2768 minus 2560, right? So again, not really a difficult concept when it's displayed out graphically like this. That makes it pretty easy to comprehend what file slack is. You would be surprised at how painfully difficult this was for some students to grasp in an online course prior to me creating this visual representation. But hopefully this helps you understand the concept of file slack, and then you can practice it if there's some lab work or some concepts that you want to this will probably almost certainly be examples of this on the final. You'll want to try to figure out RAM slack and file slack. So I hope you watch this. And now if you want to read this step by step, you certainly can. Shrink ugly professor head down a little bit there. Okay, there we go. All right, so here's step 1 and 2. You may read that, pause this and read it. I'm going to click and move on. Here's the next few steps, 3, 4, 5, and 6. If you want to write this down or take notes, pause it and read it. And then here is the 7, 8, 9, and 10th steps on how to do that. Again, pause, read to your heart's content. And it's basically everything we just covered written down. All right, that's all I've got for you. I hope that was helpful to you. Now you understand RAM slack a little bit more and file slack concepts. Now, if I were, well, let's do this. Let's do this. Let's take a look now. Take a look now at FTK Imager. Okay, so here's an example of this is FTK Imager looking at it, looking at my OS drive, and I've just got a random JPEG pulled up, alt codes. Here's what it looks like in hex mode. If I don't know if you guys knew this, if you got a JPEG highlighted up here in your file list view, it gives you the hex mode viewer. You can also go up here and switch it to text or to file viewer, and it might parse out that file, and if it's an image, it might show you that image here. So that's a nice feature of FTK Imager. These are just alt codes, like if you're, if you're doing some web design work or whatever, and or you want a special character in your your Word document or on your website, you can put in this alt code to get these special symbols. I find that useful on some of my side work. But let's see, let's take a look at this file over here under properties. Okay, so these are metadata from this file. And really pretty useful information. But one of the first things that you see up here is that it is it is 2,000 or 206,898 bytes in size. So it's 206 kilobytes in size, and it says that the physical size, and it's a little different. The physical size here is a little bit larger, as we would expect, right? The physical size is the actual number of clusters taken up by this drive, which is 208,896. So again, if I get my trusty calculator out, and I believe that my hard drive is formatted, or at least this partition is 512 byte sectors, and there's 8 sectors per cluster. I think. We could look that up also using FTK Imager, by the way. But let's take a quick look here. Let's just say I've got my physical size 208,896, and I want to divide that by 4098. Oh, right. If I have 498 bytes per cluster, then that tells me that this file occupies 51 clusters total. Now, only 50 of them are completely, well, not, you know what? No, that's wrong. Wrong in the weenie. Interesting. That should be a whole number, right? Because this is physical file size. Did I do it right? 208,896 divided by 4096. I did 4098. Okay, stupid professor. Okay, so it is 51 clusters. And that's why I was confused for a second, because physical size should always be a complete whole number when you divide by the number of bytes per cluster on your hard drive, because that's what physical file size is, as we demonstrated in the lecture. All right, so I've got 51 clusters there, so I know that the file size here, this is the logical file size, it is, even though it's only 206,898 bytes, it still is going to occupy the full 51 clusters, but there's going to be file slack in there because there's a difference. And we know our file slack on this one is easy to figure out, because we would just subtract it here, right? So 208,896 minus the physical file size, which is 206,898. So we have almost 2 kilobytes of file slack at the end of that last cluster. Of that 51st cluster, we have 1,998 bytes, which could contain surprising data, right? It doesn't. There's nothing to be surprised about in this data, but it could, in theory. All right. So if you look at the hex view here in FTK Imager, so we can see it's got this Yoya header, also has the JGIF designator, so we know it's a JPEG image. That's just file signature stuff, which I don't think we cover in this class. But anyway, if we scroll down, we're going to scroll down 50.9 or whatever clusters, and it ends right here. Now, I don't know if you guys know this, if you paid attention to FTK Imager, but FTK Imager does a nice job of breaking down your hex view into 512 byte sections. So there's 512 bytes right there. That's your first sector, and you can tell that because there's a little dotted line right down there. I don't know if you can see it on the video here or not, or the video here or not. But that's my first sector. And so we know that there are 51 of these in this file. So we just keep scrolling down. There's number 2. Oh, there's number 3. So we're just looking at sectors of information, and it's all hex encoded in plain text over here. It's all just gobbledygook because JPEG files don't really record anything in plain text. So that's what we'd expect to see, and then you get down all the way to the end. But the problem is when we highlight alt codes up here in FTK Imager, it just looks at the logical file size. It just looks at the logical data. It doesn't give us the full 51 clusters. It only gives us 50 point whatever clusters. And so then we've got to do some digging, right? So we know the start cluster of this file is 495, 498, right? And so we could actually, in theory, I'm going to try this on screen just to be super geeky. Right click, go to offset. No, I don't want to. Oh, no, not offset. Let's see if we can. Is there a way we can? There is a way. Oh, you stupid. Oh, yeah, duh. Can't do it in the logical file. Okay, sorry. Brain fart again. Wow. All right, so we're going to go up here to the partition 2, and now we're at the very beginning of the partition, and this contains everything on this hard drive, right? Well, at least that partition. And so now we can go to a sector cluster, and I don't remember what that cluster was already. I've already forgotten. Oh, it won't let me go to the cluster. You know why? Because I'm not. Let's see if it'll let me do it here. Yes, it will. All right, so let's go back one more time and see if it'll let me copy and paste that so I don't have to remember, because I'm way too lazy to write things down, because who writes things down anymore? That's stupid. Where was that? That was in my desktop. Users, user. As you can see, I have a highly individualized, and it was under media, and there it is, alt codes. And we want to go to the starting cluster here of 495, 498. I'm going to see if I can just control C that. And then we'll go up here to our OS partition and right click and go to cluster and put it in there. Yeah, it did it. Control V that right in there. And let's go, let's see, that was decimal. We want to go, that's it, decimal, hex decimal, don't worry about it. And let's see, that took us down to cluster, that didn't work. Why didn't it work? Not sure. Because it only took us to cluster 495. It didn't take us to 490. Oh, because there was a comma in there. It doesn't like commas. All right, now we're cooking with fire. All right, excellent. So we just went down to the 495,000 cluster on my hard drive, and look at this. At the beginning of this cluster, we see something that looks very familiar. Just like we were looking at the logical version of that file, this is a JPEG, so we're on the right track. And now from here, we want to set selection length, total number of bytes. I need my calculator. 51 time, oh, not divided by, gosh, 51 sectors or clusters times 4096 gives us 208,896. That's the total number of bytes. And go. All right, so now we've just highlighted 51 bytes. And, oh, I went way too far. Oh my gosh, what have I done? All right. Oh, see, I mean, when you're looking at 500 gigabytes, this is a 500, almost a 500 gigabyte partition, I think, I forget. But good luck. You move your little stupid key thing once and you're gone. All right, so let's try going again to what was that cluster? shoot, 4495489. Is that right? I don't remember. Oh, the ineptitude of it all. Golly, what a doof. Oh man, now I gotta do that all again. All right, nothing like embarrassing yourself in front of your entire class on video. Okay, real quick. I'm almost tempted to not do it just because I've taken so much of your time already, but let's do it. Let's do it. I'm going to go back to my alt codes and say that this file was, again, starting cluster 495, 498. I thought that's what I put, but well, I guess not. All right, and then back up to my partition here, and then right click and go to cluster and then put it in there and take out the comma because it didn't like that, and then hit OK, and there we are. And now I want to set my file length as 208, my selection length as 208,896 bytes, and oh, well, I didn't have it at the beginning there. Let's try that again. Set my selection length. All right, now we'll just scroll down manually, very carefully, 51 sectors, because if I try to move that little scrubber on the slider bar, it's going to go way too fast, and I'm gonna pass up 51 clusters or 51 sectors like that. Okay, so we're just gonna keep scrolling, keep scrolling, keep scrolling. And back up. Oh my goodness, this is tedious. This is tedious. Oh man, but we're already into the next file on the hard drive, whatever that is. All right. Oh, look at this. Okay, this is cool. All right. So we have here a number of sectors with 0 bytes filled in. Here's the end of that file right there. Oh, FFD9. FFD9 is in fact the file signature footer for a JPEG file. And then all of this from here down to here is the RAM slack. Okay, so that's the last sector. Here's the last sector of that file that's actually got data from that file in it. Okay, so if you look up here, you can see starting with the this byte right here, hex 37, down to the FFD9, those are the last bytes of that actual alt code JPEG. And then starting from here to the end of that last sector occupied by the file, that's RAM slack. Okay, so that RAM slack, there's nothing in there, right? Like as I expected, there's nothing that has been previously written to that area, so there's no old data from old files that have been overwritten in there. I haven't gone in with a hex editor and put in any nefarious codes or anything like that. And then starting with this new sector, which has nothing in it, right? This is the first sector of the residual cluster slack. So there's 1 and 2 and 3. So 3 full sectors at the end of that file. So 3 times 512 equals 1,536 bytes of residual slack, okay, plus the RAM slack, and that's our total number, that's our total amount of slack space, file slack. All right, and then you can see right after that file, a new file starts, and I'll let you guess what kind of file that is. It's a PNG, so some kind of other graphics file there. Incidentally, using FTK Imager, had I left all of that highlighted, we could have then right-clicked, right, and exported it out as whatever. And so let's just do that with this PNG file. I'm just going to grab a chunk of this PNG file, not the whole thing, just a little bit of it, and right-click and I'm going to copy the hex. Let's see, I should be able to just export it out. Ow, ow, ow. Oh, save selection right there. And I'm going to save it as a unknown .png. So I'm manually carving this PNG file and saving it in my UAT CFR 101 week 3 lab. No, I don't want to save it there. We'll just save it in the root of 101. Oh boy, there's some lectures. And then we'll go there and take a look at it and see, oh look, so of this PNG file, it's just barely the tip, that stuff that oh, you can't see that. Let's look at it over here. It's just barely the tip, top edge, the first few lines of resolution of what looks like some kind of a Windows API, pop-up window or something that I saved as a PNG for some reason somewhere on my computer, and the rest of it, you can see there's probably this much additional, stuff that hasn't been written to, right? So I didn't export that out. I just exported out this top. So you can get partial images and export them out. So let's say that up here in the RAM slack or the file slack, the residual slack of that first JPEG, let's say that it had overwritten an old JPEG, and maybe it was a very naughty JPEG, right? Maybe it was a JPEG of me exchanging information with farm animals or something. I don't know. And it was a criminal violation. And we could highlight that RAM slack and right click and export it out, save selection as, and try .jpeg or .png, and it might export out a partial file. Okay, so anyway, that's just something that you probably didn't care to know right now. All right, that's all I got. That was a long video. I don't know how long it went, but it was like 36, 37 minutes. We're done. Have a great week.